we'll start today's lecture with a review of Maxwell's equations. All of you have done electromagnetics at some point in the course, so this should just be a easy refresher. So the topics that we'll look at will be starting with Maxwell's equations and then go to boundary conditions. So all of you know that in the electromagnetics problem, to solve it fully, I need to not just know the equations of Maxwell, but also what are the conditions on the boundary. Okay, so these two is sort of essential. Then we'll look at power, Poynting vector, concepts like that, and a couple of theorems which you may or may not have seen in an undergraduate course, which is about uniqueness and equivalence theorems. Okay. So one thing I'd like you to keep in mind as we go ahead in this lecture and in the course is that there are equations which are written for physical quantities, okay, currents and charges. What we'll do is we'll try to generalize it to make it in a mathematical way, which will give us more power. Those equations may not always have a physical meaning, but the mathematical power that we get from it helps us to solve some problems. Now, that will be covered in, for example, in the equivalence theorems. Okay. Right. So, let us get started with Maxwell's equations, which all of you know. So, we will start with, for example, the very early experiments which, let us say, Maxwell, Hertz, Faraday, Ampere, all of these would have done, and at that time they would have worked with real valued physical quantities, because that is what you measure in a lab. You measure voltage, you measure current, right. You do not measure a complex quantity in a lab, right. That is a later mathematical abstraction. So, I am denoting these real valued physical quantities by this slightly different symbol, it's like a script E and script H. So, just to tell you that these are real quantities, okay. And so, as you saw from the previous lecture, Maxwell's equations were these four without the terms in the blue font, okay. We all know everything in the black font already. So, curl of E is rate of change of magnetic field and so on, there is a displacement current, all of that is known to us, right. So, if I look at these first four equations without the blue fonts, there is a sort of asymmetry in these equations, right, because if I look at the curl of electric field, there is a rate of change of magnetic field and no other term, whereas in the second equation there is a curl of H, there is a rate of change proportional to electric field and a current. So, there is a sort of asymmetry in it, and so to fix this asymmetry, to give us some mathematical power later on, what we do is we add two quantities to make these relations between electric field and magnetic field symmetric. And what are those quantities? If J was an electric current, then M is a magnetic current, and if rho E is a electric charge, rho M is a magnetic charge, okay. Now, as of now, we say that these are not physical quantities, okay. At least magnetic charge is not supposed to be a physical quantity, but there is actually no theoretical reason why magnetic charge does not exist. So, if any of you do find it, there is a Nobel Prize waiting for you, okay. So, that is about, so these are the equations that we will work with, okay. In fact, there is a paper by I think Dirac which says, sort of mathematically shows that there should be a magnetic charge, but we have not found it, okay. So, if you are interested, you can read more on that. Then there is another equation which is used alongside Maxwell's equations, which is the continuity relation for charge, okay. So, do you think, so that is this equation that I have written at the bottom over here. Do you think that this equation is independent of the first four equations? It can be derived, right? How would we derive it? Take the divergence of the second equation, right? So, if I take divergence of the second equation over here, if I do del dot this whole equation, so we all know that, so let us get rid of this, del dot del cross H. For any vector H, this is an identity equal to 0, right. So, that is it. Then you can see the left hand side becomes 0 and the right hand side has both the current term over here and del dot D. Del dot D we can use our Coulomb's equation and convert it to rho, right. So, this is your continuity equation, right. It is just written separately just for convenience, but it just comes from Maxwell's equations and vector calculus, okay. So, sort of to summarize, what we have done is we have introduced these two new quantities over here for the purpose of mathematical convenience and also to give us a sort of symmetry, right. Electric field and magnetic field are interchangeable. If I interchange electric and magnetic, I have to interchange magnetic and electric currents, magnetic and electric charge, right. When I convert this to a real life problem, I will make sure that I am not talking about unphysical quantities. So, one extra step I have to take care of, which we will do. Okay. It will become clear in the rest of the course how we use these properties. Okay. So, those are your Maxwell's equations, right. Let us take a simple example of how to use them. Okay. We will do much more complicated calculations in this course, but let us just take a simple wave example. So, I have written down Maxwell's equations in vacuum, okay, and vacuum which has no sources or charges. No sources means rho is 0, no and charge is also 0 and current is also 0, right. So, two simple equations. I want to combine them somehow to give me a single equation. Okay. So, these four equations we have all seen before. There are two additional what are called constitutive relation, which tell us the relation between D and E, B and H. Okay. Since it is vacuum, it is very simple. This is related by epsilon naught and mu naught. Okay. Not at all difficult. So, now if I take, I want to, from the first two equations over here, let us say I want to eliminate one of the variables, right. So, there are two equations in two variables, right. The two variables are, if I look at these first two equations, what are the two variables in these equations? R and T. No. R and T are just telling us the equations are true at some point in space and time. But at a particular point in space and time, what are the two variables that I do not know? E and H, or E and B, electric field, magnetic field. This is what I do not know and I want to calculate, right. So, that will be the general idea of any CEM example, right. I want to find out the electric field, magnetic field given some charge distribution, current distribution, boundary conditions, blah blah. Alright. So, I have two equations in two variables. So, in principle I should be able to solve them, right. So, what should we do? We will use some properties from vector calculus. So, we can take, let us say, the curl of the first equation over here, right. So, curl of E, right. Now, there is a nice relation that you know from vector calculus for this, which is del of del dot E minus Laplacian of E, okay. That is what we get. Now, of these two terms, is there any one term that gets simplified? The first term gets simplified using Coulomb's law, right, because del dot D over here, del dot D and D is related to E just by a constant. So, del dot E is going to be 0, right. So, this whole term is 0. Okay. So, we have reduced this first term. So, the left hand side has become minus del squared E. Okay. Just a quick check, is this a scalar or a vector? Is the left hand side, is this expression over here, is this a scalar or a vector? Is this expression over here a scalar or a vector? So, how can a vector be equal to a scalar? So, left hand side is clearly a vector, right hand side therefore is also a vector. Why? Because how does this guy operate? This is actually going to be del squared Ex x hat plus Ey y hat plus Ez z hat, right. So, del squared will act on each of these guys one by one and give me a vector. Okay. Del squared can act on a scalar, it can act on a vector, but right now it is acting on a vector. So, output will be a vector. So, that is one simple check that you should do, like in school we used to do dimensional analysis, right. So, this is similar over here. Alright, so I have a vector on the left hand side also, I need to simplify the right hand side, right. So, I have, so I am going to take a curl on the right hand side also, right. So, I will have minus del by del t. The del cross operator acts only in space. So, I can take it across the time derivative, right. So, I am going to have a del cross B. And then what do I do? How do I simplify further? Do I have a relation that tells me what is del cross B? Do I have a relation that tells me del cross H? Yes. Is there a relation between B and H? Mu 0, right? So, this will therefore become, so del cross B I can write as B as, I can use this over here, B is mu naught H. So, this becomes minus mu naught del by del T del cross H. Now, del cross H I know, right? Del cross H is related by this equation over here. So, this expression will become minus mu naught epsilon naught. What else? So, this will, one derivative will come from the second equation. So, this becomes del squared by del T squared. What am I left with? I am substituting del cross H as dd by dt, and d is epsilon E. So, that epsilon naught came out over here. What am I left with over here? E, exactly. Okay. So, what I have got, this is the right hand side. So, therefore, this is equal to the left hand side over here, del squared E. Okay. So, we will write this in a familiar simpler form. Let us just write, say, let us take a one dimensional example. That means the physics varies only in one dimension. Let us take that dimension to be x. So, in that case, electric field etc. is just a function of x. So, this del squared operator will only become del by del x squared, right, partial derivative with respect to x. So, if I simplify the what I have got so far, I will get del squared by del x squared E is equal to 1 by c squared del by del t del E. Okay. And this, many of you will know, is called the wave equation. Okay. Now, why is it called a wave equation? It describes a plane wave. You can see what is the solution to this equation. So, for example, if I take something like this, cos of what do I write? Kx minus omega t plus, say, let us say phi naught, right. So, when I take a derivative, two derivatives in x, what will I get? I will get back cos, right, and some constants will come. So, I will get a k squared on the left hand side. On the right hand side, what will I get? I will get E back over here. Right hand side, I will take two derivatives with respect to time. Cos will become sine, sine will become cos, I will get back cos, right. So, this will become omega squared by c squared back to E, right. So, if k is equal to omega c, then this guy is a solution, right, and this is exactly the equation of a wave that is traveling. So, is this derivation clear? So, we used very simple things, we used Maxwell's equations and all four of them were used, right. We did not leave out even one of them. We used the fact that divergence of D is 0 and the relation between D and E. We used the fact that del dot B is 0 and the relation between B and mu, okay. So, all of these relations were used along with some simple vector calculus identities, right. So, you will find that this is going to be the story of CEM. Using Maxwell's equations, boundary conditions, vector calculus, you can calculate everything, okay. And so, when this kind of a derivation was first understood, it was a very big deal, because if you look at these equations, Maxwell's equations, like I mentioned in the previous lecture, these were derived in a lab dealing with resistors, capacitors, inductors, currents. That is how these equations were derived. And somehow you are able to get out of it a wave equation, which suddenly then explains to you how light from the sun reaches us. It is coming as an electromagnetic wave. So, this connection between electromagnetics and optics really was made possible by Maxwell. And if you notice, if this term over here, if this displacement term were not here, this thing would not have worked, right. I would not have been able to get the second derivative with respect to time. This guy would not have happened, right. So, it all comes together very nicely. Alright, any questions before we go ahead? Okay. Fairly simple, many of you have probably seen this wave equation derivation earlier, okay. So, this is all fine, this is how Maxwell and company had written it in terms of real valued physical quantities, okay. Now, as it turns out, we are all electrical engineers and we like phasors. And why do we like phasors? Again, it's a simple property of electrical engineers. We don't like pain, so we want to make math easier, right? So, this using phasors helps us to reduce the mathematical complication, right? So, what I do is I take my physical quantity over here, that's E, and I write it in terms of a phasor. So, what is a phasor now? It's a complex vector. So, this is complex, and I have put the e to the j omega t, that is the phasor, okay. And this is obviously going to be a complex quantity, and since I want to only deal with real valued quantities in the lab world, so I relate it by taking the real part, okay. So, that is what we will do. By introducing this, I am also separating the role of time and space. I made it into two separate variables, and that is convenient for me with Maxwell's equations, because Maxwell's equations are nicely linear, right. So, what happens to all the time derivatives? Wherever you see a d by dt, there is a j omega that will come out and the time derivative is gone, right. So, that is what happens to my 4 equations over here. I am not writing the continuity equation anymore because it is understood. I have retained the magnetic current and the magnetic charge, keeping in mind that they are not physical quantities, okay. They are introduced for mathematical convenience, okay. So, if someone asks you what are the equations that are valid in lab, you will drop the blue terms, okay. One other thing I want to mention, which will happen to you when you read books from different disciplines. If you are reading a book from electrical engineering, the convention that electrical engineers is e to the j omega t usually. If you read a book from let us say the physics or the optics community, they prefer to use e to the minus j omega t, okay. So, you should, whatever book you pick up, make sure you go right to the beginning and see what is the time convention they have used. Both are correct, but if you get confused, all your answers will be wrong by a minus sign everywhere, okay, because of this simple difference, okay. Of course, another difference is that physicists will not use a j, they will use a I, that is another thing for the imaginary constant, okay. So, those are the phasor relations, okay. So, these are the equations that we will work with in the course, okay. Once I solve this, if someone says, okay, now give me the lab quantity, all you have to do is, supposing you solve these equations, you got some E and H out of it. What do you have to do? No, you have solved this, okay. Now, you have got your E and H has come out as a result of your calculation, and someone says, now give me the actual quantity in lab, the physical electric field in lab, what would you do? That is okay. Rho and m, the use is gone. I have already used them to solve for E and H. Now, what do I do? She says take the real part. Okay, common mistake. No, that is not enough. What else do you need to do? I have to multiply it by e to the j omega t, right. If you just take the real part of ER, you will get a time invariant quantity. We do not want that. So, remember to stick in the e to the j omega t, and that gives you the full time dependence, okay. So, those were the phasor forms of Maxwell's equations. The next thing that is used is how do I relate D and E, B and H and the current, okay. So, I am writing down these so called constitutive relations over here. So, the relation between D and E is in terms of epsilon, permittivity, right. Relation between B and H is in terms of mu, permeability, okay. And here is, anyone who knows what this law is called? Ohm's law, right. This is your famous Ohm's law, okay. Now, fields we have spoken about. Where does the material actually come into picture, whether it is glass or wood or free space, right. So, these guys and these guys, this is where the medium properties come into place, okay. What I have written is a very simplified version of material properties. In fact, in the strictest sense, these equations that I have written are wrong, and we will correct them as we go further in the course, okay. This, for example, this seems to be a simple constant. Actually, it could be a tensor for anisotropic media, and in lenses, in optics, we have that a wave travels differently in one direction than another direction. Anisotropic things are there. That is captured by making this epsilon into a tensor or mu into a tensor. Okay. There are further complications with these equations, these constitutive equations, and I'll point them out when we come across. Okay. So these are the main sets of equations that we will work with. All right.